started. So in this part, we'll talk about where the idea of neural network came from, and show you like the connection with the biology of neural networks. And this will be the content of this section. It's part 2A, means almost chapter 2A. Okay, let's get started by learning how do our brains work. So let's see how our brains are working. So machine learning involves adaptive mechanisms that enables computers to learn from experience through examples. So now this is a common knowledge in machine learning. So when we talk about machine learning, we know in machine learning you do have set of examples that you are learning from, and these examples are translated to be the actual uh, model that can be applied later on unseen data. So machine learning came from the adaptive mechanism, adapting a set of examples that will enable the computers. We know computers are working based on software, so they use software to operate. Now, the experience that we refer to in here is the training data set. So remember that we have trained examples, and this trained examples is the data set that we can use for learning a specific model or capturing or training a specific machine learning model. So these learning capabilities, they improve the performance of intelligent systems. So these capabilities of adapting on a specific experience. And it can evolve over time, which makes them more efficient and accurate. So when we talk about efficiency, we're talking about time and space and performance and more accurate in terms of results with each iteration. So iteration after iteration, you train on more data, increasing your data set or fine-tuning your models. So by that time, the performance gets improved. The most popular and successful approach to machine learning draws inspiration from the nature itself. So we're talking about where the neural network idea came from. It came from the nature. And when we talk about nature, we are looking about a neural or artificial neural networks in the human brain. So when we look at the human brain, we should be able to see some neurons, and the neurons are distributed across the human's body. And this is where the idea of neural network or deep learning came from. So the neural network algorithm, it in fact mimics or mimicking the structure. So we're looking about the structure of the brain. The brain contains like some components and cortex, and this cortex also spans to neurons. The neurons can be very long, that for example, from your finger toe, up to your brain. So we are looking at the structure, how it's being built, and the functionality. How does it function? Some functionality comes from the brain, some is local functionalities. And the idea in here, we are mimicking the same structure in the biology and the functionality in the biological neural network that we have in the human being or in animals in general. So we can create systems that are capable of remarkable feats of pattern recognition. So we are looking for uh, pattern recognition and recognizing and learning certain patterns and making some decisions. So the main idea came from the artificial neural network functionalities as well as structures, as we'll see in a minute. Let's dig deeper into the human brain and see what's the human brain and how does it work and what are the main components and functions that we have in the human excuse me brain. So let's get started with the brain structure. So the brain consists of interconnected modules. These interconnected components or modules, they are performing complex information processing. And this is what we do. You are looking at something, your vision is capturing some information, your brain will process it and come up with reactions or processing operations that include sensory. So we're looking at sensory, like either touching, smelling, seeing, all of the sensory of a human. These sensors or sensory senses for a human being, they are acting as an input for the analysis. Like for example, you are touching something that's smooth, or you are smelling something that has a specific odor or smell. Then what happens is we do have a memory storage within our brain. that will save this information, and it should be able to retrieve it, bring it back when we have something similar. For example, if you have an experience with a specific smell, then what happens is when you are smelling it again, that will be retrieved from the memory, and it can make some reasoning like if else reasoning. It does have some emotional processing, like when you feel something, you are happy, you are sad. It does have consciousness as well. Now, if we look at the brain in here, and this is what you see in on the right-hand side, so we see it in the form of manifolds. So these manifolds that you see it in here, the goal of it is to increase the surface. So increasing the surface that the brain has. So it would be in the form of these manifolds. So it's like you are tucking in certain clothes within a small area. And to make the surface much larger, you'll just fold it, make it in manifolds like what you see in here. Now, this is mainly the functionality of the brain. Let's see how the neurons within our neuron system are working. So neurons in biology, they are the basic computational units. So they are the main like unit, functioning unit within the human like a neurosystem. The neurons serve as a fundamental computational element. So whenever I'm looking for something or smelling something or touching something or feeling something, this will be processed within my neurons of the nervous system. So the nervous system is the system that will act or interact with the surrounding environment and react upon that. It will do the thinking, and it does like recognizing things, retrieving information from the memory, creating reasoning, and it does have the emotional processing. So these specialized cells, now we are talking about the neurons. The neurons are cells, and they're among the largest cells in the human body, are heavily interconnected. So when we talk about the neurons, like if you look at the human neurons, you will see that they are connected, like, and they are connected to the brain again. So these are heavily interconnected, with each neuron potentially connected to thousands of others. So each neuron of this might be connected with thousands of others, like they are distributed across your or the human body, creating an interact web of information. So we are talking about web in the form of a spider web, like a huge, massive connections and interconnected or densely connected network that will have information flow throughout the brain. So it will carry out the information from like sensories or from human body parts to the brain. Now, this is when we talk about the brain, now we realize that it's this brain, and we do have these neurons that you see on the right-hand side, and they are heavily connected with each other as well as the brain. This will create sort of in parallel type of processing. So this will create a parallel processing. And since we talk about thousands of neurons in the human body connected to each other, we are talking about massive, huge parallel processing within the human body. And this will create 10 billion neurons. A typical human brain contains approximately 10 billion neurons working simultaneously. They are working at the same time. So when we talk about 10 billion neurons, this is a huge number. And when you think about how they are coordinated and how they are working together, how they are processing simultaneously, so this is a huge processing. It's massive processing. And this processing happens simultaneously in parallel. So it happens at the same time for several types of operations. And then we have the network architecture that builds this nervous system. Neural architecture, we have neurons form an enormous interconnected network enabling complex cognition system, so cognitive system that will recognize the surrounding environment and interact with the surrounding environment. Now let's look at it and magnify at the different anatomy and functions that we have within the human brain. Neuron structure, we learned that each biological neuron consists of three main components. So we have each neuron, it does have three main components. The first component is the cell body. Remember that we talked about it, it's a big cell that might span across the human body. So it's a cell. So the neuron contains the cell body. we refer to it as soma. Then we have the axon that's for signal transmission. We have nervous branches. We call them dendrites for receiving input from uh, other neurons. So let's look at a picture quickly in here to learn more about the structure. So we're talking about the cell. This is the cell body or the soma. Then we have the axon. So this is the axon that carries the information from cell to cell or transmitting the signal. And then we have these dendrites that we talked about, like you can see it in here, like these small branches that will connect and receive information input from other neurons. So let's get back in here. So this is the main structure of a neuron. Now, the neuron has a binary state in here. And this binary state, we refer to it as one of two states. Well, the first one is called firing. So if you look at knowledge-based systems or expert systems, when we have a rule, when we execute the rule, we call it we are firing the rule. So firing, that means you are sending a signal from one neuron to another or to the brain. So you are sending signals. So sending a signal from one neuron to other, and the signal will be in the form of electrical signal. So it's electrical pulses in the human body, or it's either firing, sending, or creating some sort of signal, or it will be resting, inactive. So it will be either active or inactive. It's just in resting state. So this binary nature forms a foundation for neural computation. Why is that? Because remember, our computer deals with either there is electric or no electric pulse. So 0, 1 in computer corresponds to 1 corresponds to firing, and 0 means resting. And if we look at it in time intervals, it will be mimicking exactly how the computer works, or the computer works mimicking this exactly. Threshold activation. A neuron fire only when a total incoming stimulus. So stimulus, that means something that will stimulate it, will activate it, will make it act from all connected dendrites. So remember the dendrites as we described them, they are the actual branches that the neuron connects or used to connect with other neurons, exceeds a critical threshold value, implementing a natural decision-making mechanism. So the firing process, it won't be at any signal. It will be if there is a specific threshold, and the threshold that we have, let's just say T. If the signal is greater than or equal to this T, then the signal will be activated, or we will have firing signal. Now, synaptic transmission. Synaptic transmission is the thin gap. So it's like if we think about like this is the dendrites, and this is one dendrite, and then we have it's connected with another neuron. So this is neuron 1, and this is the neuron 2. They are connected with each other. Now there is a small thin gap between neurons axon and another dendrite. So this is what we are talking about. This gap in here is called synapse. A signal exchange occurs there. Now, when a signal happens in here exchange, it will become in this thin layer of the synapse through neurotransmitters with varying synapse strengths determining the connection efficiency. So this is how the exchange of signals will happen. Now, let's highlight on some of these terminologies again. We talked about key biological components, as we see in here. We talked about the dendrites. So the dendrites, as we have seen them, they are these small portions that we see in small branches that we see them in here. So these are the dendrites. Like you can see them, I just circled a few of them. And so they are the input receivers that collect signals from other neurons. Typically, they are in the form of 10,000 connectors or connections per neuron. So we talk about a huge number of dendrites in each neuron. And then we have the cell body. So it's like any other cell. It does have a nucleus, and it's a central processor that integrates incoming signals and determines whether to fire or not. So it's like the brain of the cell. The axon, it's the output channel. So we're talking about this exon. So this is the exon that we see it in here. It's just a long channel. It's the channel that transmits electrical pulses, excuse me, spikes to downstream the neurons when activation thresholds is exceeded. So we're talking about if a signal happens and it's above a certain threshold, as we have seen it in the previous slide, electric pulse will be transmitted from one neuron or from one neuron to the other one, and this will be carried on in this exon. The synapse is a chemical junction. Junction, that means a connection. So we're talking about, like, again, as I described it in here. So it's a junction. These are synapses, and between neurons where neurotransmitters enables signal transmission with variable strength. So we are transmitting information based on the strength of the chemical signal that has happened, which results on electrical signal. Now, some of our learning objectives in this part of our class, so we are looking into mapping the biology to artificial intelligence. We wanted to understand where the idea came from. We wanted to identify what artificial neural networks are and understand weight summation, grasp the activation functions in biology, and then recognize some of the limitations that we have using some examples like the XOR example. Now, the artificial neural networks and the mathematics behind it. Now, if we try to magnify and look at artificial neurons and find what's the mathematical model behind it. So from biology to mathematics, let's look at it. And an artificial intelligence or artificial neuron transforms the biological model into precise mathematical operations. It receives multiple inputs. So I'm talking about this is neuron, it's just called N1. It does have some components, dendrites and exons and other components. So what happens, it receives, remember that we said each neuron is connected to thousands of other neurons. Now, this neuron, it receives input from other neurons in the body at the same time. Remember, we talked about the massive parallel computation. So we are looking about, for example, this is N2, neuron 3, neuron 4, neuron 5, neuron 6, neuron 7, neuron 8. Like if you look at your hand, for example, and how many neuron you have, and how many dendrites you have, and how many signals you can receive, and send to the next neuron, and so on and so forth. So you see in here, this neuron, N1, is connected to 7 other neurons from N2 up to N8. Now, when an input comes to a neuron, and this neuron will gather all this information and send it to the next, or take the signal and send it to the next neuron next to it. So what happens is, like a specific neuron, it receives a multiple input. So they are referring to them in here in the form of x's. I refer to them as n's, each multiplied by a corresponding weight. So what happens is this. Now, if you see these neurons that we have, now what happens is this N2 does have more impact than N3, for example. So what we do is we multiply it by weight 2, and this one we multiply it by weight 3, and this one weight 4, just to amplify it, make it stronger. This is W4, this is W6, and this is W7. So we multiply it by a weight, and the weights are variables. They varies. It depends. Like for example, if this one is stronger, that means the weight in here will be much larger. Now, this multiplication, what happens is the neuron, the input to neuron 1, what happened to it, it will be calculated in the form of what we refer to as Z. And this Z will be the weights, the weight of each neuron that we have as an input for N1 times the weight. So the input times the weight, W times X, plus B, which is the bias, some sort of bias or error. We'll talk about it later on. And this can be translated to how many neurons we have in here, which will be N, and start from 1. This will be the weight times the X, which is the actual neuron signal, plus the bias, which will be the input to this neuron. Okay, now, like if we wanted to translate this one into matrix multiplication, and there is a reason why we translate it to matrix. This will be translated as W's transpose times the X. So we are talking about like if we have a list of weights in here and we are multiplying them with a list of X's. So this will be translating into W transpose. So this is W and this is the X's. So this will be W transpose times the X. And this is matrices. And when we talk about matrices and why we do it in matrices and convert it to matrices, because matrix is parallelizable and we can apply parallel in it very quickly. So you can do a lot of calculations very quickly. So where W transpose X is the weight sum. So this is the Z weight sum. B is the bias term. We talk about it. We talked about it before in here. We will talk about it in more details later on. And phi is the activation function producing output A. So we are talking about in here. Phi is the activation function that we'll talk about it. We have a chapter about activation functions in neural network, and this will calculate the A, which is the final output that we will have for this neuron. So the bias term B allows the neuron to shift its activation threshold, providing a crucial flexibility in learning complex patterns. For example, if you look at this, we do have a curve like this. You can shift this curve up and down, move it this side or this side by this bias that we have in here. So it enables more flexibility. Now, what is artificial neural network now? Let's just look at it in a different perspective and try to summarize it. We have nodes or units. So remember that we have seen in here. So you have this is one node. Let me just use the blue. This is one node, node. Each one of this is a node. And these nodes are what we are referring to. They are units in here. They are processing elements. They are like, if you think about the computer, you are looking at the brain, which is the CPU. The CPU has cores. So think about these units or nodes as the cores with input and output. Each neuron has input and output. Remember, like this is what we have seen. And one, it does have 7 inputs from all these, and there is one output in here or multiple outputs sometimes. So there is input and output or outputs, each performing simple computations. So each one of them is performing simple computation. When I talk about simple computation, you have seen, excuse me, what happened in here is just multiplication and addition. We did not do any complicated mathematics. So each one of them is doing very simple, sometimes we call it primitive computation via specific node functions. So we are not doing or performing any complicated mathematical computations in here. They are just primitive basic computations. So weighted connections, we talked about the weighted connections in the previous slide. So we do have links between the nodes, and these links, they are carrying specific signal or signals with connection weight determining information flow strength. If you remember, I talked about the strength, which is the impact, which one has higher impact. So this is why W's are in here. If I increase the value of W, like let's say this is 10, this is 1, 1, 1, 2, 1, 3. So this will tell me that this neuron has the highest impact, which is 10. So this is the strength, which is the weight. The network architecture, and this is extremely important in our context. When we talk about an architectural design, we are talking about the number of nodes, so how many nodes I have, and how they are connected to each other. So it's the structure and the connectivity, the nodes, and how they are connected to each other, pattern primarily determining what network can be or what the network can compute. So this is, we refer to it as the network architecture, which is the number of nodes and how the nodes are connected with each other. Simplified abstraction, a highly simplified computational model inspired by the animal nervous system. So we talked about this simplified architecture that have been taken or inspired, like taken from the nervous system of a human being or the animals in general. Now, let's try to compare the artificial neural network with the biology one. Artificial neural network is the deep learning that we are learning about, and the biological, which is what we see in animals or in human beings. So, the artificial neural network Let me just make sure. Okay. The artificial neural network, which we refer to it as ANN, and the biological network, we refer to it as BioNN. Now, the inputs, the nodes, sorry, they have input and output units with node functions. So there are certain functions that they are calculating, the activation function, for example, where the cell body in biology, it receives signals, determine firing frequency. So this is what we see in biology, whereas it's nodes in artificial neural network. Now, in the biology, we have synapses. Synapses are the junctions, the connections that we use to connect different variables or different synaptics, and then they pass the signal. They pass the chemical signal. Whereas the corresponding one is the connections in artificial neural networks, and they have weights. And these weights, as we said, they determine the strength of each um, neuron input. Links with adjustable connection strength, which computed or controlled by the weights. Computation. In computation, artificial neural network is the mathematical operations. And remember, like it was very basic and primitive computation. It's a weighted sum, which is a summation of weights and values. And that will and then we will add them up together. So this is summation of weights and values plus activation. Remember, we take the output of this weighted sum and with the bias, and then we feed it to activation function. We'll talk about the activation function later on. Learning weight adjustment through algorithm like backpropagation. Now, these weights that we are learning in here, how do I optimize them? How do I find the best value for each one? So they are being optimized using learning mechanism. And the learning mechanism that we have is sometimes it's called back propagation in neural network. And the computation within the biology, it's electrochemical signals. It comes from chemistry that has been translated into electric, that signal integration and firing. So they are just set of rest and fire as we learn. The learning in uh, biological neural network, they are synaptic plasticity and the structural changes within the actual neuron, whereas in here it's just through the back propagation. So they share, both of them, they share some similar things, like for example, parallel processing, massive parallel processing, which is what we have seen in here, like when we translated this into matrices. Remember that this is W and this is the X, and we can just calculate them in parallel. Fault tolerance and the graceful degradation operates in pattern direction manner. So it's just from the neuron itself back to the brain, and critically rely on learning and adaptation. They are adapting and learning from a former experience. Now, let's look at the key capabilities or the strengths. Why we believe that neural network is very powerful, because it does have some capabilities, some strengths that we will learn about. So, for example, learning from examples, which is the idea of machine learning. So we are learning from examples. So we do have list of examples, either images, some text, and other types of data. So neural network can learn complex patterns um, and relationships directly from data examples. When I talk about relationships, it can be among data examples or from X to Y target, if I'm talking about supervised learning. So it can be in supervised learning or unsupervised learning with appropriate learning methods. So we do have learning methods as we have seen it in the previous slide, something similar to gradient descent, for example. Eliminating or backpropagation, sorry, eliminating the need for explicit programming. So you do not need to create exact coding for this learning. It will be implicit. Inspired by biology. So this has been inspired by biology. These systems models reasoning based on the human brain architecture. So it's very similar to the human brain, how the human brain is functioning, using complex networks of simple computing elements working in parallel. And this is key. Just keep this in mind. So we're talking about primitive or simple computations that happens in parallel. Now, collective intelligence as I said, they are simple individual elements. Like think about it like you do have a complex problem or a job that's a huge that will take you a month to finish. If you get 10 more people, it might take you like, for example, 3 days or plus minus time. So it's a simple individual elements. They are combined to perform sophisticated high-level operations, demonstrating emergent computational properties beyond a single component. So it's collective work. It's not just a single person or a single thing that works. It's just a group of things that are working together in parallel. Now let's look quickly at the history of neural network, where it was started in 1950. The perceptron has been introduced, which is the first trainable artificial neural network, sparking initial excitement about like machine intelligence. So that was in 1958. Then in 1969, AI winter begins. So we started seeing some more complicated, like for example, we used or some scientists used perceptrons to solve problems like XOR, which is revealing the fundamental intelligence or limitations and causing uh, funding decline about the neural networks and perceptrons. Then in 1986, scientists came up with the idea of backpropagation, and remember that we talked about backpropagation a few minutes ago, and we will have a dedicated chapter about backpropagation. And this backpropagation is being used for training multi-layer networks. So when we talk about a network with multiple layers or components, you need something like a method for this training, and backpropagation is one idea for training these multi-layer networks. 1998, CNN has emerged. Lee Kong developed the first Lee net for digital recognition or digit recognition, sorry, which is the handwritten, if you remember numbers like Mine's data set, demonstrating the power of CNN, convolutional neural networks, and how they are powerful and how their accuracy is fairly high. Around 2012, AlexNet appears to solve the problem of ImageNet as we described it in the previous chapter, which proved that deep learning superiority and launching the modern AI era. Then in 2017, Transformers has appeared using something like attentions and GPT and BERT. Now, if you remember in 2012, why this has had like a great progress, because more computational power has appeared, like GPUs. We'll talk about them in a separate chapter. Now, this is a brief history. How's the development of neural network from 1958 up to our today's date, which is we are using GPT and BERT models. Now, let's get into the idea of neural network. The main idea is we are looking about separability. Separability, it means you do have multiple classes, like for example, in this chart, what you see in here, we do have two classes, red and blue. We are looking for this line that separates the two classes. In our case, in this example, it's very simple. It's just a linear uh, line. Sometimes if we have, so this is 2D, if we look at 3D or 4D or 5D, so we're looking at more of a hyperplane. And sometimes this hyperplane is much more complicated than just a simple linear line. So the perceptron's limitation, a single layer perceptron can only learn linearity separation, which is what we see in here. And remember that we in the past or in the introduction, we talked about like there are relationships much more complicated than just the simple linear separation. And single layer perceptron, they are just learning this linear separation. So this dividable by a straight line, or even if we talk about straight line is just in 2D, similar to this one. But if we have more than 2D, we are our higher dimensionality, we are talking about a hyperplane. Now, the famous XOR problem. So XOR problem, something that you guys learned in computer skills, demonstrate its fundamental limitations. No single line can separate the XOR function output. So if I look at the XOR functionalities, I have input x1 and x2. It's like digital gate. So you have x1 and x2, two inputs. When you feed them, you'll be learning certain pattern in here. And this is what we have learned in here. So we have the input is 0 and 0, the output will be 0. So this is like false and false. This is the truth table of the XOR. The output will be false or 0 and 1s. So this is false and true. The output will be true. So this is not, this is like the OR in this line, for example. If I have 1 and 0, it will be 1. 1 and 1, it will produce 0. So, so the pattern in here is much more complicated than a simple linear separation. So if I try to create a linear separation to separate the values based on the input x1 and x2, this won't work. So I need a little bit more complicated methods rather than just simple linearity with a single layer perceptron. So what we need to do is we need to introduce more non-linearity to learn more of non-linear separation between between components. So why this matter? The XOR problem motivated this development of multi-layer network. So we are talking about XOR as an example. So it's not the only example. We don't care about the XOR per se, but we are looking for more complicated problems that will be nonlinear, similar to what we have learned in the DA 360. You remember we talked about decision boundaries. So decision boundaries are the boundaries that we have in here that separates two classes from each other. And how can we learn more complicated or non-linear decision boundaries like circles, for example, or sort of a zigzag or something like that? We need multiple layers. We need to stack them. Stack them, that means put them on top of each other in the form of a stack, like how you are organizing the plates or so. Now, this gives us a good motivation that we need a little bit more complicated models that can capture decision boundaries, and these decision boundaries, they are non-linear, which is what we see in practical life. So decision boundary in very special cases is just linear. And in practice, in most of the cases, it's always non-linear. This brings us that a neural network can be used in multiple types of problems. For example, it can be used for supervised or unsupervised learning. It can be used for generative models. It can be used for reinforcement learning. So remember the different types of machine learning algorithms that we have learned in the previous, excuse me, chapter. So in supervised learning, think about it like the teacher is teaching their students and they are providing them with reward when they are learning something good. So in supervised learning, we are thinking about classification. In unsupervised learning, we are thinking about or referring to clustering. So in classification tasks, we know classification, we do have data, and we do have the target, the labels, and we are trying to learn or associate the data, find patterns, so it will be uh, preparing or producing the correct labels. So training set required, and some real world applications like classification of emails as spam or not, or legit, medical diagnosis, and so on and so forth. Now, if we wanted to think about it from simple Python code, like if you look at this example in here, so this decision boundary is much more complicated. So we have four different classes, sorry, and we wanted to find a decision boundary that separates these four different classes. So if we go with a very simple, like for example, linear model, it won't be able to capture the decision boundary in here. Now, what we have done, we tried to create simple perceptron weights and created some plots to show us the example that we have in here in the form of scatter plot. Now, the perceptron or single perceptron won't be able to capture the nonlinearity. So we need something that's much more complicated. Why XOR requires the depth? The depth in here means the stack of layers. So we are thinking about stack of layers. Layers more than just single layer. So stack of layers. The XOR functions cannot be solved by a single perceptron. We talked about this because it requires non-linearity decision boundary. However, by adding hidden layers with two neurons, each learning different linear boundaries, their combined output can be used by a final neuron to correctly classify all XOR cases. If we think about the XOR as a classification problem. So now we added more than just simple neurons. These limitations of perceptron motivated the development of multi-layer perceptrons. So what we described in here is you do have two neurons, and these two neurons, they are connected to one other neuron, and now we are able to learn the complicated decision boundary in multiple layers. So now we have multi-layer or multi-layer perceptrons. We refer to as MLPs, and ultimately modern deep learning architecture. And at the end of the day, we are looking for this deep learning that we refer to it as. I usually refer to it as a modern machine learning architecture that we will explore in details in the following parts. Now we have linear separation or separator, which we learned about in, for example, it's a simple line or simple hyperplane. Two hidden neurons, they are learning much more complicated patterns. The XOR points is much more complicated. So we do have in the middle some other types of models that we can also learn. That was about the classification or supervised learning. Let's look at clustering or unsupervised learning. So an unsupervised learning is just grouping. You are looking, you do not have any labels. You wanted to group objects based on certain patterns. So this is what we have. Like if you do have certain shapes, you wanted to group them together and you do not have labels. So clustering algorithms, they group together objects that share similar characteristics without predefined labels. So we do not have labels. Data is unlabeled. The network discovers natural patterns and a structure within the data. So it will realize natural patterns and certain structures within the data. The optimal number of classes. So we do not know how many clusters we will have, but the optimal number of clusters depends on the specific problem that you are solving and data structure. Now, one common example or business case that we use in clustering is marketing. So, like you wanted to find how many, for example, how many customer segments or sectors of customers that you have. You do not know what their behaviors. You wanted to find how many sectors you have, so you apply some clustering on this data. But should generally be kept as small as possible while still capturing the meaningful distinctions of the data. So this is what we need to do. We need to find this K, which is the number of clusters, and we wanted to keep it minimal as possible, just to find the best number of clusters. Now, objects within the same cluster should have similarity other than objects within outside of the cluster. So this is something like I think you all learned about it in the past in other classes. So our goal is just, so this is cluster one, this is cluster two. Our goal is to find the furthest or increasing the distance between the clusters and reducing the distance within specific cluster entries. Now, conceptual check, let's just look at our understanding. Why do we need the bias? We talked about the bias in here, just moving the data up and down. What failed in XOR, linearity and nonlinearity, and what does the activation bias? The activation will also add to us the non-linearity. And we can combine multiple or multi-layer networks together within that linearity. So now the perceptrons that we talked about is just the basics. The basic idea that we use for building a deep learning architecture. Now we will see how we are moving from perceptrons to deep networks. So perceptron, it was just a single neuron or a few neurons next to each other. Now we wanted to get it more complicated. More complicated, that means we are learning better decision boundaries. Remember that decision boundaries that we talked about? So our goal is to learn more complicated. The goal is not to complicate it, but decision boundaries that can capture complicated patterns. So we talked about single neurons. we have learned how an individual artificial neurons compute weighted sum and apply the activation function. Now, network limitation, single layer network can only solve linear separation or separable problems, which is like very simple linear challenges. Yeah. Failing on XOR, for example, and any other non-linear task, which is very common. Non-linear tasks that are very common. We need to add the depth. Depth means increasing the number of neurons. So you do not just have one neuron. So you do have multiple neurons like this. So this is the first layer. This is second one, third one, fourth one. Each one of them, it does include a set number of neurons. So we need a multi-layer. So you see in this example, we have 3, 4 layers with non-linear activations. Each one will end with non-linear activation function, and that can learn arbitrary nonlinear decision boundaries. Our goal is just to learn this nonlinear decision boundaries as we describe them. Now we'll talk about this in part 2D, and we'll learn how you can create multi-layer perceptrons, backpropagation, and create more of a deeper networks. Now let's see also how can we use neural networks. So we learned we can use neural network, for example, for supervised learning, unsupervised learning. You can also use it for vector quantization. And this is something you guys will learn more about it in natural language processing. Remember that when we talked about text, so we know our machine learning models cannot understand text. So how can we deal with text? So we need to convert it to bag of words, for example, translate each word into the corresponding number. So the machine learning models can understand these numbers. Now, what would be the best way to represent these numbers? And how can we deal with or handle synonyms or handle semantic similarity, not just the syntactic similarity? Neural network can be used also for extracting what we refer to as word embeddings. So we call it word embeddings, which is mainly what I was referring to as numbers, vectors that are representing the words in text, and it's an application of natural language processing, and it's sort of features, high quality features that can capture the semantic in text. You also can use it within images if you wanted to find a compressed type of representation for your images. You can use a neural network, and we will talk about it later on in this class. How this work, you train a model, and this model can be used for extracting this quantization. You can also visualizing these regions, and this is something that can be used also for identifying some important regions within your vector. uh, Now, going to another application, we can also look at forecasting. Remember that we had classification. Classification um, is just identifying like what would be or predicting the class, predict a specific class of a data point. Now, in the classification, this classification is a single point. The input is a single point. Whereas when we talk about data that's associated with time, like for example, I wanted to forecast the weather. Now I wanted to know how the weather will be tomorrow. What's the temperature? What's the humidity? Will it rain or not? Now, what I will do is I'll take the input will be the past couple of hours or couple of days or last year or 3 years or 4 years. Now I'm looking at time. Now, the prediction in terms of time, we refer to it as forecasting. If I do not have time, it's mainly prediction. So one idea also how you can creating a prediction, market trend prediction over time. Like if I look at this and this is time, I can look at how the market is trending. Like this is seasonality, we refer to it, and ups and downs. Like for instance, this is Eid, this is another Eid, this is another Eid where the sales or the profit is being increased. So now, this is another application that we can use neural network with it. Now, let's look at the key characteristics of a neural network. So the main characteristics of artificial neural networks models The core characteristics is the connectivity. We talked about the connectivity, heavy connectivity. The input of one layer is an output of the previous one. And there is like one neuron can have multiple inputs, and it can have an output that goes to one or more neurons. Value types, input and output values can be binary. Remember, trigger, we have rest or firing, or bipolar. It can be -1 and 1, or continuous values, enabling diverse format of information. So it can be handling like images, text, and other types of information. Activation timing, all input to a node are processed simultaneously. Remember, like I have, like for instance, this is a layer, this is a second layer. So this is a layer, and this is a second layer. I can process this one at the same time as this one, this one. Once I'm done with this layer, I can process these three in parallel. Imagine this is not three, these are 3,000. So you can process 3,000 at the same time. And once you are done, you need to move to the next layer. And the same thing, this can be processed at the same time. So activation timing, as I mentioned, can be done in parallel, which is a huge improvement. I mean, if you look at it from time perspective, this will be a perfect parallelization, and it will make our training much faster. Weighted links. We talked about weights, and they are providing an importance of a specific neuron, and this can be learned, as we said, using back propagation. Conclusion and takeaways. We learned how we have been inspired from biology in building our neural network. It does have huge capabilities and some limitations, and it's the foundation for our deep learning. In the next class, we will talk more about artificial neural network. I will try to expand it more on deep learning. Thank you so much.